Night settles over a courtyard in wartime Moscow. Snow hangs in the air like powdered chalk. Behind blackout curtains, a laboratory hums. A glass bulb vibrates on a wooden bench. An engineer in a threadbare coat leans close, watching a needle twitch on an oscilloscope. He turns a dial. The bulb sings, invisibly. A wrench left on the table trembles until it creeps toward the edge and falls, clang, onto the floor. Outside, anti-aircraft guns wait for the next raid. Inside, a different weapon is imagined. Not steel or fire, but pressure, air, and resonance. A cannon made of sound. This is the story of a Soviet weapon that never fired, at least not on a battlefield. It begins with a wartime question that crossed borders and ideologies. Can sound alone destroy? The Second World War is an age of machines, but it is also an age of waves. Radar stalks aircraft by microwaves. Sonar hunts submarines by echoes. Radio stitches together fronts thousands of miles apart. In this age of invisible forces, some engineers wonder, if waves can find an enemy, perhaps they can stop him. Across the front line, Germany experiments with devices the press later calls sound cannons. In labs and sheds, engineers tinker with resonant chambers and explosive mixtures to generate blasts of low-frequency pressure. After the war, Allied technical teams sift through prototypes and sketches, proof that the idea had occupied minds, if not battlefields. The results are underwhelming. The devices are huge, fragile, and short-ranged. The concept does not vanish, but it does not mature into a weapon of decision. On the Soviet side, acoustics is not a curiosity. It is work. Even before the war, physicists and engineers in the Academy of Sciences focus on sound, how to measure it, shape it, and put it to use. In 1931, the Soviet state forms an acoustics commission inside the Academy. During the 1930s, laboratories in Moscow study musical acoustics, speech, and the physics of waves. When war comes, those disciplines do not go to the shelf. They are conscripted. The Soviet Union fights for survival on a continental scale. It also fights in factories and laboratories. As cities evacuate eastward, so do research institutes, packed into train cars with their transformers, vacuum pumps, and crates of glassware. In those relocated rooms, scientists study everything that might save a soldier. How to clear magnetic and acoustic mines from rivers and ports. How to locate enemy batteries at night. How to hear a submarine in a freezing sea. Questions about acoustic power, about how loud loud can be, naturally arise. Engineers already know sound can move things. It can shatter fragile objects or heat gases. At certain frequencies, it can drive resonance. At certain intensities, it can damage tissue. But a weapon is more than a laboratory demonstration. It needs range, repeatability, ruggedness, and a way to point force at a moving target. By 1943, Academy groups begin circulating internal reports on high-intensity acoustic generation. These are not newspaper features or public lectures. They are classified memoranda and drafts, the kind that speak in numbers, not slogans. They discuss horns, gas drivers, sirens, and piezoelectric stacks. They analyze attenuation, how quickly sound dies in air, and how humidity and temperature swallow different frequencies. They calculate the size of a mouth to project a wave at a distant object, and the energy costs to keep that wave coherent. They list targets: light metal housings, fragile relay contacts, unarmored optics. In some versions, even human physiology. But under every line of possibility, the engineers scrawl hard caveats. Air is a poor conveyor of destructive energy. Pressure falls with distance. The bigger the horn, the harder it is to aim. The higher the pitch, the faster the energy dissolves in the sky. Some later accounts claim the Soviet Union built a prototype acoustic cannon in 1944 and mounted it on a truck for trials near Moscow. These accounts often appear in popular press, memoir fragments, or interviews decades after the war. They rarely include a design drawing or a test log. No wartime photograph of such a cannon has surfaced in public Russian archives. Several researchers who requested files from Academy repositories have found references to acoustic generators of great power, but not to a deployed field device. The best supported documents describe intensive work on acoustic minesweeping, the opposite of a cannon, and on sound ranging and sonar. The weapon remains a corridor rumor wrapped around genuine high-power acoustic research. Whether or not a single prototype rolled into a snowy field, the physics problem does not change. Imagine you want to crack a delicate instrument panel on a truck at 100 meters. You can choose low-frequency infrasound, which penetrates obstacles and can disturb the human inner ear, but requires enormous moving air mass and giant horns. Or choose ultrasonic beams, highly directional, but quickly absorbed by air, especially in winter moisture. Either way, the power budget balloons. You must feed the beast, compressors, combustion drivers, heavy electrical sets, in a country rationing copper and fuel under bombardment. One engineer scribbles in a margin, "All of this to do what a single rifle can do?" But engineers do not always work under a single mandate. Wartime research often travels in clusters. You study one thing because it might aid another. The same math and apparatus for an acoustic cannon overlaps with what the Navy desperately needs: devices to trigger or spoof German acoustic mines. Those mines lurk near harbors and river mouths, listening for the sound signature of a ship's propeller. The solution is not to silence every ship. It is to make a machine louder than a ship in the frequencies the mine craves, and tow that machine ahead of a minesweeper. If the mine cannot tell the difference, it explodes harmlessly, far from steel hulls and human hands. Here, Soviet acoustics shines with practical results. Engineers design robust noisemakers, hydroacoustic emitters that endure cold, vibration, and salt. By late 1944, such emitters become standard kit in several fleets, especially on the Caspian and Volga flotillas, and later in the Baltic. Crews learn the practice. Vary the frequency. Tow at set distances. Let the device take the blast. Factory workers align coils with cigarette-stained fingers. Sailors wire straps tight against winter decks. These are devices of sound, built not to destroy with waves in air, but to fool a trigger underwater. In a way, they answer the same wartime question from a different angle. Sound can be a weapon, but more reliably as a lure than a hammer. In land warfare, sound also matters in less spectacular ways. Soviet artillerymen, often outgunned in the war's early years, need every tool to locate enemy guns. Sound ranging, arrays of microphones, time measurements, and triangulation helps them fix positions at night or through smoke. It is not glamorous. It is the patience of reading waveforms on paper scrolls. But it saves shells and lives. When observers speak of acoustic weapons, they often overlook this, the quiet offense in data. Still, the idea of a sound cannon lingers. It lingers because it is simple to picture and difficult to execute. And that tension is the essence of wartime invention. Consider human targets. High-intensity sound can cause pain, disorientation, and, at very close range, damage. But the battlefield is not a test chamber. A soldier can crouch, turn away, or place a wall between himself and a horn. Sound, unlike a bullet, wraps around obstacles and thins with every meter. The same property that makes sound a wonderful messenger makes it a poor projectile. Engineers study mitigation as hard as they study attack. They test ear defenders. They model the resonance of hull plates. They add damping to instrument racks. In aviation plants, workers learn to knit felt liners and apply rubber mounts to cancel vibration pathways. In tank factories, as welders finish a seam on a heavy plate, someone taps the hull and listens, like a musician tuning a drum. If we cannot be silent, the logic runs, we can at least be stable. There is also the matter of secrecy, real and perceived. In the Soviet Union, wartime science reports were rarely public. After the war, the Cold War sealed many boxes with fresh wax seals. When the 1990s arrived and some archives opened, researchers found treasures and gaps. For acoustics, fragments appeared, institute histories, memorial articles, and internal bulletins mentioning powerful acoustic radiators, gas-driven sirens, and piezoelectric assemblies of large area. They also found proud accounts of minesweeping achievements and sober assessments of failures. But no order to field a sound cannon, no tactical instruction, no photograph of a parabolic horn glaring across a snowfield. The weapon, if it was ever built, never left the lab. Contested. Did Soviet physicists plan to use acoustic pressure to disable aircraft on approach? One recollection, published decades later, suggests a proposal to site high-intensity sirens near airfields to vibrate delicate engine components. The proposal made it to a committee. It also met the winter air. Calculations showed that even if a siren could vibrate an engine casing on a test stand, turbulence, distance, and air absorption would ruin the effect in the sky. The idea was filed away, perhaps with more than a hint of relief from the airfield crews. If this sounds like the slow death of a dream, remember, most wartime science dies this way. Not in scandal or folly, but in careful arithmetic. The real romance is elsewhere. In 1944, a young acoustician writes home from a relocated lab that he is learning how to hear the sea by numbers. He says the equations are like listening with your eyes. He does not mention cannons. He describes the smell of hot varnish on a coil, and the way the clamps of a test tank leave a cold groove in the metal of a bench. He believes he will return to music after the war, and he does, in a way. by helping build the Soviet Ocean Acoustics program that maps sound channels in the deep. The genuine legacy of the weapon that never fired is not a secret gun. It is a continuity of craft. The post-war Soviet Union becomes a powerhouse in physical acoustics, in underwater sound, architectural acoustics, and vibration control. Academic journals fill with studies of waveguides, scattering, and transducers. Institutes train generations who design everything from sonar arrays to concert halls. The wartime habit to measure first, then dream, never quite leaves. Meanwhile, myths accumulate around the blunt phrase acoustic cannon. Some myths borrow from foreign stories. Others embellish real Soviet work with dramatic claims. This is not unique to sound. It is what happens whenever science is secret and memory is long. For the historian, the remedy is not cynicism. It is patience. If a weapon exists, it leaves a trail. Drawings with dates, requisitions for unusual materials, field trials with observers and signed failures, a dose of bureaucracy. That trail, for a Soviet sound cannon, remains faint. And yet, the emotional pull of the idea is understandable. It is the same pull that makes radio seem magical, and an echo in a well feel like a voice. In a war of steel and fire, something is haunting in the thought that air alone could be shaped to harm, a breath turned into a blow. Across cultures, sound has always held power over the body. Drums to steady marching feet, horns to frighten horses, music to calm or enrage. Modern science adds numbers to those intuitions, showing how a wave can push, heat, and confuse. But numbers are also a shield against fantasy. They tell you whether a horn must be the size of a house or whether a power plant must follow it with cables like roots trailing a moving tree. Let us return to that twilight lab in Moscow. The engineer wipes frost from the inside of the glass. He and his colleagues are not villains and not wizards. They are problem solvers inside a siege. They test gas-driven sirens, monstrous cousins of factory alarm bells, watching gauges bounce as back pressure builds. They arrange arrays of quartz plates, soldering them in parallel to drive a larger diaphragm. They take notes on absorption coefficients. They curse a valve that sticks. They try again with a thicker gasket. When their numbers disappoint, they do not toss the work away. They translate the data into something useful. That siren's throat geometry, useless for a cannon, becomes a better air raid siren in a factory district, saving seconds on a cold night. The quartz stack feeds a generator for a new ultrasonic cleaning rig to strip oil from bearing races, shortening a bottleneck in a tank plant. The damping compound meant to resist a hypothetical sound beam makes a radio chassis last twice as long on a rutted road. In war, the line between weapon and tool is narrow and full of switchbacks. As the Red Army crosses the Dnieper and later the Vistula, scientific committees shift focus. There is less time for speculative projects. The Academy chases immediate needs: ballistics tables, de-icing chemicals, rocket propellants, optical glass. When the war ends, the secrecy thickens again, but not around acoustic cannons. It thickens around the bomb, the missile, the code machine. Sound returns to its quiet empire: the ocean, the theater, the factory floor. The aspiring cannon recedes to a footnote. Estimated, Somewhere in a storeroom, there may still be a horn with a split seam, a crate packed with felt and stenciled "Do Not Drop," a notebook of faded green pages with pressure readings from a winter afternoon. If they exist, they document something less than a weapon and more than a rumor. They document curiosity under pressure. For a channel devoted to secrets and their shadows, perhaps that is the right scale. Not the triumphant unveiling of a wonder weapon, but the honest anatomy of a near miss. An idea that engineers tested until it drew its own limits in pencil on graph paper. The Soviet sound cannon belongs to that family of wartime phantoms, machines that make sense in stories and struggle in the air. And yet, the question that birthed it still echoes. Can sound alone destroy? Today, militaries around the world use high-intensity acoustic devices to warn, to deter, to disorient. They are not artillery, they are instruments, loudspeakers with intent. In laboratories, acoustic power shapes materials and moves droplets with levitation. It images organs and crushes kidney stones. The same wave that fails as a weapon at a distance triumphs at a millimeter. In that sense, the wartime engineers were not wrong. They were early. Back in the courtyard, the snow has stopped. Morning is a gray ribbon behind the smokestacks. The engineer returns the fallen wrench to the bench. He tightens the clamp on the resonator and writes a number in the margin, underlining it twice. He does not know how his notes will be read in 50 years, whether they will be filed under weapons or under industry or lost. He only knows the war will ask him another question tomorrow, and that answer will begin with a measurement. The story of the Soviet sound cannon is less a tale of a secret gun than a map of a discipline under extreme conditions. It shows how an army of physicists and technicians pursued every path that might shorten the war by a day, even paths that ended in a cul-de-sac. It shows how myth grows in the cracks between secrecy and memory. And it shows, most of all, how waves, patient, invisible, stubborn, can change a war without ever firing a shot.